Hello, good afternoon. Thank you very much for inviting us to present. I am International Managing Director in Socotec. My background is in structures, and this is why I will explain more or less what we will see here. I will try as well to do a holistic view of whatever we will explain, and hopefully you will like it. So these are the different case studies that I will try to explain. Hopefully we will have time to go through all of them. And I will try to present you the pathology at the beginning and how we solve the design of the structure or the problem or the building or whatever we have. The first one is a pathology, but it's not a typical one. In Spain, we have regulations in terms of urbanism and rules. And in that case, this is a building that they have to keep the facade to do the refurbishment inside and then create the building as a new structure, but inside of the facade. So we were retaining the facade and doing a new building. As soon as the structure was done, the council revised the maximum height of the building, and they realized that it was too high. So there was an option here to say, okay, I need to reduce the building. I need to reduce only the roof. I need to demolish one level, whatever you can do. The architects came to us with the developer, and we decided we can help you to cut the building and make it shorter. So in that case, what we decided, or what we explained, was a different step process to cut the pillars, to cut the cores, disattach from the facade, and then squeeze the building. This is a very abnormal pathology, but at the end could be a pathology. We couldn't do it on the top level because if we squeeze the building only at the top level, then the building becomes unusable on this top level. So we were able to decide with the architects which were the best levels to do that. One is the level number 6, and the other one was the top floor. Okay, so here you can see the process. But whenever you do something weird like this, you need to take into consideration that you are cutting the building. So the horizontal forces need to remain stable. So that's what we need to put this bracing in the middle of the building. We need to do cuts that transfer the loads with artificial elements that you will remove afterwards. And you need to use jacks to do that. And we need to have one jack. Well, this is all the steps. So I think that we shouldn't go to all of them. But here you have all the floor of the building, all the floor view. And you can see that there are cores, there are columns, there are elements that support the building. So we need to do one device per each element that is sustaining whatever you have above, okay? At the same time, because we built the building already, the building was connected to the facade. So we need to detach the building from the facade again, do all the process, but retain the facade because all the structure that was retained in the facade was already removed. So we need to invent devices to keep the retention of this facade. So these are all the drawings for all the details that were developed to do that. And here you can see more or less, sorry for the quality of the pictures. We are engineers. We are very bad taking pictures on site. And that's what happened, okay? But here you can see all the elements that were placed on the roof just to retain the facade in place, okay? Here you can see as well that each column has different rivers, different reinforcements, different loads. So each of them, it was classified in 3 or 4 different types to be able to define these details that were able to transfer the load to this device and then to the jack and then to the existing column, okay? So here you have more details. Not everything is in here, of course, but here you have some of the pictures. You can realize more or less the picture is very bad, but the device that is attached there, then you have the bracing and another device here. Luckily, the loads were very low because the building was empty. Just the structure, just a little bit of use load, but we were able to transfer the load directly through the slab. We don't need to do another transfer on the upper level, on the upper column. So it was quite easy, more or less, okay? Here you have more devices like this with the jacks, right? So how we do the transfer, and as you can see, there are different types, depends on the type of load, depends on the type of column, and as well, the core. The core is a big element that needs to be as well settled, and you have to do it at the same time. So the picture is very bad, but you can see the core, how it's transferred to the elements. And this is the cut that was made on the core. And how you do one of these cuts. So the same that you use to drill the elements on the slabs, it was used horizontally to put there an element to cut the whole core. We place the jacks there, and then you drop all of them at the same time. That was made in the middle of Barcelona. I don't know if you have been there, but it's the diagonal, the main street. So 414 is next to Passeig de Gràcia, which is the place more expensive in Barcelona, but no one knew. It was behind of the existing facade, so it was hidden, okay? But we drop everything, and here you can see how on the left, that's before the settlement, and that's after. So as you can see, the difference between the existing connection with the slab and the new one, it was quite relevant. That's why we couldn't absorb everything in one level. Okay. Another one from London that all of you know, this is a pathology that is not very common too, but it's very interesting, which is that this is a building that it's heritage. It's fully protected. It was bought by British Land a few years ago, and they were doing the refurbishment of the entrance. As soon as they were doing the refurbishment, we were working with local engineers, that is Evolve engineers, and suddenly the building control said, no, you cannot proceed. Why? And the problem was that the whole structure, the whole steel structure on the roof of the ground floor is not painted with intumescent paint. So suddenly, without the pathology is without the record drawings or the record project explaining why they were able to not paint the steel structure, we had to demonstrate how to do it or paint it. But this is a heritage building, so we cannot start painting with intumescent paint something that is protected. So what we did here was to analyze the building, the steel structure, with a CFD model, so computational fluid dynamic analysis, to understand which were the temperatures that we can reach in the case of a fire on the structure. If this temperature is lower than a certain level, there is no problem because the steel can remain with all faculties, okay? So we defined per the place where we were doing the job and the overall ground floor, a fire case there that is red and a fire case there. So we defined the different specs for each fire to understand which was this level of heat on the top. So this is the criteria to say that if we are on more or less, you can see the blue line that is on the top. This is the percentage that you reduce the capacity of the steel. Because in case of fire, you are an accidental fire, an accidental situation, that means that you can reduce the safe coefficients, okay? If we're able to reduce the safe coefficients, that means that we can reduce the capacity of the steel. And that means that because of the temperature reducing the capacity of the steel, we can match both lines and say, okay, if we are at 300 or 400 degrees, the steel remains capable to resist. So we model the whole ground floor. This is the axis that we were doing the refurbishments. And probably you recognize that here on top goes all the ring, okay? Or the arch. And this is the simulation that shows the beginning of the fire and the end of the fire. As you can see with colors, the temperatures here, if we are below 350, below 400, we are fine. So the color in yellow is just happening on the floor, but not on the top. So the level of temperature that we reach on the structure is quite low. We can as well analyze how everything is moved, not only the fire as well the smoke, because the smoke has temperature and you need to be careful with it. And this is more or less the affection on plan view of the fire. And as you can see, it cannot even arrive or reach to the glass, okay? So this is the scenario of the temperatures that we reach on the fire, right? The theoretical regulations tell you need to follow the red line. And I put this image because it's quite interesting to see that a real fire is a combustible thing that burns and ends because the combustion finishes the combustible. So the theoretical one that is on the regulation is the red one. So that means that goes very high and never ends. And in reality, everything drops. And if everything drops, means that at a certain point, like timber, for example, the quantity of combustion is reduced. And this is the real temperatures that we reach in one of the beams that are up there. It doesn't matter which is, okay? But all of them are below 300, okay? So we are not reaching the level where we must be worried in terms of steel capacity. Another one. This is an industrial building that is located in Madrid. This industrial building was bought by a foundation from France that is called Carasso Foundation, and they decided to do their own foundation. There is a work space, space to share with people. So it's a very interesting reuse of an existing building. The building has not many value, honestly, because it was quite generalistic, so nothing to protect. But in that case, it was interesting to keep the essence of the building. So the client wants to keep everything as much as possible and reduce the carbon footprint and do something very, very sustainable. The problem is that you receive a building that is for industria, and there is no insulation. There is not too many capacity in terms of comfort for the people that is working there. The protection from the sun in Madrid is nothing, and in Madrid it's very high. All the back part of the building that is industrial, that is, well, the behavior for the people that is down there, it's not very good. But additionally, doing some numbers, because we did a due diligence first, the building was not stable. There was a war in terms of stability. So we have to reconsider everything. In that case, that's Madrid. We are in the south of Madrid, but in the center, let's say, and we are just here, very close to the train station of Atocha. So that's the facade of the building. This is a Google image. And as you can see, it was more or less an industrial building with the offices on top. And then we had the back part, which is all this, let's say, warehouse that, as I said, in terms of insulation, in terms of thermal performance, was not good. So here the pathology is that whatever suits in the industry is not suitable for an office space or a common space for working. And additionally, the architects were trying to do something without using air conditioning. Madrid is a very dry city, and what we tried to do was to work with the evaporation cooling effect. So if you spray water, the water evaporates, and in the process of evaporating and changing phase, take heat from the air, and then you feel much better. And because there is low humidity in Madrid, when you increase the humidity, you are more comfort, right? These are more or less the state of the art of the building. These are the roofs. So the building was, well, not very good. And this is the proposal. And so you can see they occupy an industrial space to do and to manage many other things that were not used at the beginning. So in the front facade, we place a facade to protect from the sun, as well to do some gardening, to increase the humidity, increase the capacity of the building. Then we have the back with the big warehouse. We have the roof with PV panels combined with vegetation that performs much better for the PV panels and for the green. On the lower part, we have a gathering place with these stairs and these places. So there is a huge change in terms of thermal performance, but as well in the structures, because the tower of the building was simple connections. And honestly, we didn't know how that was standing up there because it was relying only on the brick walls, okay? So we did a lot of approach in terms of design, in terms of reducing the impact of the building and how we can do refurbishment. At the end, what we decided was to play with this kind of solar protections, having the radiant floors. So what we did was to increase a little bit the screed of the radiant floor and put cold water or hot water connected to a geothermal energy on the ground, on the warehouse part. And that was very interesting because Madrid has a very good soil to do that and a very high water table. So the combination of both make very efficient the ground source heat pump. Okay. As well, the fresh flow and the heating flow was very good in Madrid because you never will have condensations because the humidity is very low. So in terms of comfort, was a good achievement. This is the whole section. As you can see, we collect the rainwater. We have the ground source heat pump. We have all the solar protection, production on the roof. Even though it's very VAT oriented, we decide to go for it anyway. So at the end, we had a building that was much more sustainable than it was, keeping the structure, so all the materiality as much as possible, because the facade, we add things on top more than destroy whatever it was. So in terms of carbon, we did, or in terms of energy as well, we did lots of analysis on how we perform much better on that it was, which is that it's what we need nowadays. So whenever we do a refurbishment, what we need to obtain is an action that reduce the energy performance that it was before, and that we don't increase the quantity of carbon emissions for the building, or at least we can compensate in a period of time with the savings in terms of energy, right? So here you have all this excellent performance that we have nowadays with the new building is nearly to 50%, so that's very low. And in terms of consumption, 14 kilowatts per hour per square meter. This is a passive house building, if you want, without following passive house. In terms of CO2, as you can see here, these are the way everything is distributed. So we have structures, facade, we have the ceilings, the partitions, the facade as well, and the floors. And in terms of the whole carbon, so we did as well the accountability for the CO2. As you can see here, we have a reduction at the end for the whole thing of 52, which is much lower than expected by the foundation. And we are very proud of it, because at the end, we are doing 240 kilos CO2 emission per square meter, which is under what is requested for Leti, for example, okay? They are in a target of 300, 350. So the idea is to have a building that performs much better, that people is in comfort inside, that we use less energy as possible, but as well that the demand is lower. So here, the key point was to reduce a lot the demand of energy. And then the last case, this is a proper refurbishment. The pathology of this building, that it was abandoned for more than 30 years. As you can see, the facade is plenty of different paints. Here there is one. Here, I think there is another one. So depends on the season of the year. You have one or another one. It was occupied by people. And that was the first building in l'Eixample. L'Eixample is this kind of nice distribution that you have in Barcelona with this square of streets that has these chambers. And that was the first one of the grid. And it was abandoned for a long time, but as you can imagine, is highly protected, okay? So that's after the refurbish. So that is done. As you can see, the building now looks nicer. The lower, so the business on the lower part is still on site, so it's not finished. But the idea was that we did a site visit. We did the structure and the MEP. The building was absolutely destroyed. It was plenty of pathologies, plenty of cracks, plenty of things. Because it was abandoned, that was more, let's say, remarkable. And then in terms of the state of everything was quite horrible. But it's the only, or probably the unique building that is in l'Eixample that respects an old path that was going through this place here, okay? And for several reasons that we really don't know, the town has kept this idea that you need to respect this place, but you can occupy the back of it and the front of it. When we did all the analysis for the building, we saw that this building was not stable enough as well for the new regulations. So Barcelona has changed the seismic capacity or the seismic loads that you need to resist. And because this building was fully refurbished, we need to comply with the existing regulations. And because we were doing all the reinforcements and everything, we had to comply with the existing ones. So what we proposed with the architect, and the architect was very happy about it, was to eliminate the core inside of the building and move it to the back, just to this corner, and then use this core to retain the building, as well as having extra floor for apartments. So the idea was to do something that was more easy to do a better space. Here you can see the old path. Okay, Antiguo Camino de Ronda, that's the name of the path, and that's what we need to respect. But it remains something on the back, which is this purple color, that we use for the new core, okay? And this new core provoke all these footbridges from the core to each apartment. But you avoid on the apartments, the corridor, the stairs or the elevator, okay? That was the idea. Of course, this core, the new core, needs to be fire protected, needs to be resistant as much as possible in terms of fire and all this stuff. So these are the architectural floors. As you can see, we kept as much as possible the structure of the building because we were doing new loads on the building and the building was refurbished. We need to comply with new regulations. We did a proper geotechnical report. All the house has been piled with steel piles on the ground. You will see the details. These are all the structural drawings for reinforcing the foundations, the typical floor, how it has been reinforced with the brick and everything. We work as well with the elevations, as you can see here. So this elevation, there is a tricky thing on the right, but most of it has been preserved, which is the back one, you will see now. But the inner one has been changed a lot because we were removing the core from it. And then these are the elevations on the sides that has been changed a little bit as well as that one to have something to retain the building because it's quite slender. And this is the core on the back where we have the stairs. The details for the steel piling for the foundations, even if it is a wall or if it is a column or whatever it was. And then the pictures of the building, how it is now. And you can see that even on one of the pictures, we have a swimming pool on the roof. So it has improved a lot, even though it's an existing building, is the oldest one. And we have all these fancy and nice systems to connect the building with the rest of the flats. Well, they have these kind of things exposed, which is fine for us. And this is the pool. And as well, they want to be quite sustainable. There was another company involved with the sustainability, so to make the building very sustainable. And one thing that they did was to, let's say, redirect the sun inside of the patio. Otherwise, it was quite dark because the building is very high compared to the narrow part of the path. So that keeps the space at least natural lighted. And now they have as well some planters there that has been grown, so that the vegetation is much nicer. And that's it.